Today is the second day of this event, and in this session, Professor Nitesh Purohit will deliver a talk on the promising technology for upcoming wireless networks. Dr. Nitesh Purohit is a professor and dean at Indian Institute of Information Technology, Allahabad, Prayagraj, UP, India. He is an author and reviewer of reputed publications like IEEE Transactions, IEEE Journals, IEEE Signal Processing Letters, Elsewhere, and Springer Journals. He is a co-author of the book COVID War, UP Model Strategies, Tactics, Impact. Dr. Purohit has delivered more than 60 invited talks in various FDP conferences, workshops, including a few motivational talks to meritorious school children under Inspire and NASI fellowships. As principal investigators, co-investigator, he is contributing to many government-funded and consultancy projects, transferring 3D printer technology to Indian telecom industry, Mankapur. Its commercial production has been started. Viral, FOPIS, STI Hub on ICT are some of his well-recognized projects. As National Coordinator of the Flexible Academic Program, FAB, he is working towards implementation of National Education Policy 2020. He is the channel chair of the orientation camp, which aims to inculcate ethics, values, and nationalism among IIIT Allahabad students. He is the editor of the proceedings of Orientation Camp 2020, Flexible Academic Program, and a few international conferences. In past, he contributed to IIIT Allahabad as head of EC department, associate dean R&D, associate dean admission, assessment, and award, member of International Affairs Committee, nodal officer study in India program, chairman CCLCAA Ordinance Draft Committee, member of IARC, member of Institutes Advisory Committee. Further, he is an external member of Academic Ethics Committee, IIT Kanpur. He is a senior member of IEEE. Now I welcome Professor Nitesh Purohit sir to deliver his talk.
Thank you, Satish, for the nice introduction.
Thank you, sir.
So let me first share the slides.
Yes, sir.
So I hope my slides are visible.
Yes, visible, yeah.
Okay, thank you. So I'm really honored to be here, and I am really thankful to the SRM University Andhra Pradesh, Vice Chancellor, other administration, the organizers of this FDP program, and Dr. Satish and his entire team. Thank you for inviting me, for giving me this platform of sharing a few thoughts. So in this talk, I am going to cover, you can say, tip of the iceberg of a few technologies under the heading that promising technologies for upcoming wireless networks. And primarily, I have read this particular article. This is the title of the article, written by the Professor Mehdi Benis, and it appeared in IEEE Spectrum magazine in December 2021 edition. And there was a really interesting way of placing a few facts under this heading that if 6G becomes just 5G plus, then we have made a big mistake. Now, this is something a very catchy title, and I read this particular article. And then when Satish called me that this is a FDP which is supposed to happen on this recent advancement in wireless networks and networks. So I thought that this is the topic which I should address. This is so interesting, I find. And this is so fundamental. At the fundamental level, every communication engineer knows it well that it is the Shannon who has written a paper in 1948, after which the entire communication engineering starts changing, and actual change started around 1980s or so. So switching from the entire analog domain to the digital domain, and what are the advantages and other things associated with the digital communication, there is no need of elaborating it. But it is really interesting that the time Shannon framework is accepted by the communication engineers, and if we concentrate ourselves focused on wireless cellular networks, then we can see that okay, first generation was the analog FM based communication network, so it is out of scope of discussion. But from the second generation, which is the GSM standard, and the third generation, which is the CDMA standard, or the fourth generation and the fifth generation, which is still under deployment, if you see that all of these different generations of communication, cellular, wireless networks, definitely there is some leading technology associated with each one of this generation. There is the TDMA here, CDMA here, OFDM and VoIP is the very important aspect of this 4G, which is definitely continued in the 5G. But one thing which may be noticed, that all of this network from second generation to 5G, and in fact the 6G, most of the groups are talking about that what should be there in the 6G. This is precisely in line with this Shannon's era model. So there is no change at the architectural level, at the fundamental level, if we are talking about. And this is precisely what Professor Mehdi identified and explained in that particular article. And yes, it was not the first article. There have been some other articles prior to Mehdi. So the important part of the entire communication system theory is definitely surrounded about Shannon's work. And Shannon is a legend because in 1948 itself, he has identified that the communication is something which should be identified with 3 levels. So these 3 levels of communication, or the problems with the communications, are actually identified by the Shannon himself in the same paper. And the entire work of the Shannon, what we are calling it as a traditional physical layer, this is nothing but this is only this problem which was picked up for the elaboration by Shannon. And this level B and level C was definitely out of scope at that particular point of time in the 1948. But interestingly, no further development could have been done even after 60-70 years. So this is precisely what Professor Mehdi pointed out, that if we have to actually move towards a significant change, then we have to start from the fundamentals. We have to look at the fundamentals. We have to see that where are the fundamental problems and how can we solve it. So if you just look at this particular system, almost it is there in every communication engineering book. We know today that the transmitting end, there is the source, and then we are having the source coder. We are invariably doing the channel encoding, then modulation, and then RF transmitter, and then we are transmitting. And this is the way we are receiving the information. And everyone knows there are various ways of doing all these things. And we have been doing it in the second generation, third generation, fourth, and fifth generation. Exactly same thing we are doing. In a different way, in a much modified way. And that's why we are getting the better efficient systems, more bandwidth, and you know that there are several features. What we could not have done in the 2G and 3G, we have done it in the 4G, voice over IP. In fact, it is an all IP network. And we have seen that what are the benefits which are available. We are using all these things. So apart from the benefits, if we just see that where these technological developments are not changing, where they are using their own traditional ways. So you will identify that these three aspects, generation of the information, then transmission of the information, and the usage of the information by the end user, these are being separately treated. Even in the 5G. The current 5G specifications, most of you have seen. Even in the 5G, this aspect is as it is. Whatever was there in the 2G. And why it is so? Because it is the Shannon's frame. Shannon developed the framework like this. The digital communication systems which were developed for the wireline system or the wireless system, they are following this particular model. And that's why this has to be there. So the argument is simple, and one example is given over here. In the Shannon model, we all know that it is the probability of occurrence of the symbols which carries the information. Less probable is the symbol, more information it is carrying. So if you just think of a simple example, someone is randomly pressing the keys of any system, any computer, any mobile, anything. So from system point of view, if you look at the information content of this particular message, definitely it is very rare and huge amount of information is generated. So accordingly, the system is going to assign more resources to this particular message, which is actually useless. So why it is useless? Because it is not carrying any information as such to the end user. But in the Shannon's sense, this carries a lot of information because it is inversely proportional to the probability of generation of message. So this is something one need to understand, that the technical problem has been more or less perfectly solved by Shannon himself and the researchers which have been working on the Shannon's model. And now the time has come when we must look at the other two levels of the problem which were identified by the Shannon himself. So what is the level B is precisely what I was talking about in this example. How precisely do the transmitted symbols convey the desired meaning? And this is something which is the semantic problem. So in this case, as far as the technical problem is concerned, a highly informative message was transmitted and received, but at the semantic level, this message has not conveyed anything. So solving the technical problem is a good part. Technical problem, that is a level A problem. That is how accurately you can transmit the symbol from one end to another, from source to destination. But what is more important is definitely this semantic problem, that how precisely the information that user want to convey from source end to the destination is being conveyed by the symbols which are carrying this information. So it is one level up. And most interestingly, Shannon has defined another level over and above this, which is known as the effectiveness problem. That even after this message has been conveyed, how effectively this has been understood. That is also very important aspect. We are teaching in the classroom, and we know that every student is not grasping the same thing from the lecture. So it depends upon the receiving end as well. Only semantic 100% transfer of the information at the syntactic level or the semantic level is not enough. One need to look into the effectiveness as well. So for most fruitful communication system, one need to look into technical problem, semantic problem, as well as the effectiveness problem. So this is something at the first place one need to understand. And this immediately transforms into a requirement that these three aspects cannot be treated separately. One has to think of the unification of these processes. And more interestingly, this unification cannot be arbitrary. So we will further take it up. But first, let us have a look at what is there. What are we calling as a 5G plus? Then we will again come to this part. So we know that in the 5G communication system, there are two technologies which have been experimentally tested and incorporated in the standards. And it's not new. MIMO is something which was not there in the 3G, but in the 4G it was suggestive, and some development was there. But in the 5G, you will find that it is an integral part of the system, and that's why we are saying. And since it is working fine, so we are expecting it in the 5G plus system as well. Similarly, artificial intelligence is something which has already been incorporated at the upper layer, and we know that in the mobile edge computing, where we are talking about the micro clouds and the regional clouds and the cloud level computing, these things, a lot of artificial intelligence has been used. So artificial intelligence and MIMO. These two are integral part of the 5G system, and these are supposed to be further refined and upgraded. In fact, if we talk about the 5G and MIMO, then one may identify that worldwide 5G is being implemented in the lower side band around 5 gigahertz. So whatever we are implementing is MIMO only. But actually, maxi MIMO is also suggested, and for its implementation, it requires that the 5G implementation should be done at the higher frequency bands, suggested bands of 50 gigahertz and 60 gigahertz and so on. As of now, it's not there. So one of the technology which is continuously improving since its you can say since its development, its identification, and now I can club this with a new heading of antenna channel combo. This combo is something which is being used in different places. So I have used here because antenna itself cannot do, and the channel itself cannot do. It is the combination of antenna and channel which is able to bring gains for the communication systems. And these gains, when we are talking about, these gains are in terms of diversity gain, or it may be in terms of the multiplexing gain. But gain is available. And this implementation is possible if we have the complete information about the channel in both ends. Unfortunately, there is a technology which we call the space-time coding, or multi-code is there, very famous, which is also a part of the 5G. And spatial modulation is another technique. I was seeing your schedule, and I find that actually one dedicated lecture is there on the spatial modulation, and there you will find out that this is so interesting way of implementing this antenna channel combo system. Very interesting technology. So what is important to understand that how this technology works. And you will find that it is entire mathematics. In fact, entire communication system is governed by the mathematics. Probably entire communication system. So you will see that it is very simple. If a transmitter has multiple antennas and the receiver has multiple antennas, that's why we are calling it the multiple input and multiple. Then the channel is actually having a matrix. And if this matrix can be decomposed like this, then we can definitely weigh the input and weigh the received vector such that this can be eliminated, and what remains is only the independent channels. And that's why we are saying that it is just the virtual base. And that's why the importance of the maximum is there. More and more antennas can be here, which can have a matrix which can be decomposed like this. And that's why the higher frequency range is required. If we are trying to put large number of antennas and operating at the near frequencies, at the lower frequencies, then there will be a lot of issues, and this bifurcation could not have been possible. So this theory is there, this practical implementation is there. It's already a part of well-tested system. It is definitely expected to be a part of the future technologies. A little bit of artificial intelligence, I have already told you that it is something which has already been incorporated at the upper layers of the 5G. In fact, at the physical layer as well, it's some you can for the network modulation and other parts, a little bit of application of AI is there. And I'm going to talk more about AI applications. But before this, I would like to draw your kind attention on this particular article. I recently read this article, published on January 2022. IIT Delhi professor is there, and this is a very interesting article that how false love for AI/ML is destroying our engineering college. Everyone is talking about the AI. Everyone is trying to teach the AI, and without actually going into that mathematics which is there, and it is creating the problems. So yes, AI is important, as I said. It is an integral part of the 5G system. It has a very good future, very bright future. A lot of things we are looking to be done by the with the help of artificial intelligence, machine learning techniques. But this is the question. Everyone need to understand this, that it is required to be learned from the sketches. You need to know the entire mathematics before using a particular AI. This is also a very important topic, and I have seen this is also a topic which is supposed to be covered by another speaker. So I am just introducing this. A very potential 5G plus technology. And whenever I am saying 5G plus, it means the performance of these technologies will definitely be better in terms of making available higher bandwidth to the user. And that's why 5G plus is there. And here also the idea is very simple. So there are reconfigurable intelligent surfaces. Just a schematic diagram is being shown over here. There is a transmitter, and simple first principle is there. There are so many pitches over here. When we are at the receiving end, the signal may be directly received, may not be directly received. In most of the antenna, most of the mobile systems, generally this is not available. But what is available is a signal which is coming from reflectors. So idea is very simple, that whenever these reflectors are designed in such a way that they can form a desired beam, they are a part of this communication system. This is very interesting. Before this concept, we have been considering these reflecting surfaces in a different way. So what is being suggested over here, since we are having the metamaterials and we can control the reflection characteristics by simply controlling the characteristics of these metamaterials, why shouldn't we use it for benefiting the communication? And that's precisely what is being done over here. Since we are also having the channel state information, without this memo cannot be implemented. So this channel information can also be used for configuring different patches of these reflecting surfaces, and that's why we are saying it is the intelligent surfaces. What intelligence is there? reconfigurability. So these surfaces, or to be more precise, the elements or patches under these surfaces may be reconfigured based on the channel state information such that desired beam formulated. And this is something which is truly a promising technology. Now, this is something which is also coming up in a big way, because security has always been a great concern. And the mechanism which has been adopted to address this security problem has a lot of issues. For an example, if we see that the current approach of cryptography, then this cryptography is based upon this assumption that the adversary has limited computational power, which is not true as on date. Because a lot of computational power is available, easily available to anyone. So cryptography is definitely not have you can say a future. It has to be changed. How it will be changed, what will be changed, I'm not sure. But one thing is sure, that cryptography is something which is required to be replaced. Why it is to be required to be replaced? Because of this thing. This assumption does not valid anymore. So when we have to switch from cryptography, another such technique which is known to us is the spread spectrum. And everyone knows CDMA, third generation system, everyone has studied, frequency hopping, everyone has studied. So it is definitely a physical layer technology. This is the upper layer technology. But it is also having assumption that the receiver does not know the spreading sequence. Although in the CDMA third generation system, it was not used for this particular purpose, but we know it can be used. In fact, in the defense, it has been used for a long time for this particular security purpose. In the third generation system, security was not the reason, and that's why this spreading sequence was known to everyone in the public domain. It's a different way of implementation, but as far as technology is concerned, spread spectrum is a technology which can be used for security purpose. But the assumption is the receiver is having the limited knowledge. So this also belongs to those technologies which may not have apparently a long run. And that's why this newer concept, although I am saying newer, but you can see over here that in the 1975 it was first proposed. But no as such much attention was paid, there was no need for it. And for the kind of technologies which were there, spread spectrum were more than enough for the security purposes. But nowadays, the kind of technology that we are using in the 4G and 5G and the later future generation networks, I guess that these two will not work, but one need to fall back on this physical layer security concept. So the features of this physical layer security is it is at the physical layer. It does not have any assumption on the adversary's computational power. It does not have any assumption on the adversary's available information. It is definitely provable, quantifiable, and implementable. So it is something a field which requires proper exploration and proper incorporation in the future generation systems. And 5 different ways have been identified. This is something I have picked up from a survey paper. These are the reference number over here. But the more important is, what are the different approaches in which this physical layer security can be implemented? So these are the 5 ways. It may be information theoretic security. It may be artificial noise headed security. It may be security oriented beamforming. It may be diversity assisted security approaches. It may be physical layer security. And you can see over here that a lot of work is available in each one of these, and nothing is enough. A lot of scope is there. A lot of scope for work is there. So let me share the fundamental. What is this physical layer security? And if you know a little bit of theory, the information theory, then the things will be clear that how it works. So we know that this is the legitimate sender and this is the legitimate receiver and this is the eavesdropper. So what we want that this entropy, conditional entropy, should be equal to the entropy of the source. That is, the receiving of the message Z should not have any increase in the information at the end of this eavesdropper end. And that's why this is being, this entire communication is required to be designed in terms of this, keeping this secrecy in view. So I'll give you another example, our own work. We did this work recently, and you can see this paper available at the IEEE Transactions in Vehicular Technology. So this security I am continuing. Before this, I would like to point out another very important technology, which is also I am looking as a 5G plus technology. And this technology is known as the two-way relay. And our research group at IIIT Allahabad, Prayagraj, we have done a lot of work in this particular technology, two-way relay. Several problems, mathematical models we have put forward, solved, and published. But here I am presenting it in continuation with the physical layer security aspect. This paper is about the same thing. So the model of the wireless channel, wireless tape channel is something like this. And our model was something like this. We considered there is a transmitter with several antennas. There is a relay with the single antenna, and there are so many receivers over here. So in the two-way relaying system, in the first phase, you can see that it is the solid line. In the first phase, the information or the message is simultaneously transmitted by this end and this end to the relay node. So if there is some eavesdropper somewhere, in this paper we consider that we do not know where it is, which is the factually correct position. We never know whenever we are communicating where the eavesdropper is. So he definitely receives this information. And in the two-way relay system protocol, this is then, it is the AF system. So it is then again amplified and broadcasted so that everyone once again receives this thing. So this information is available to the eavesdropper. This information is available to the eavesdropper. And under this condition, what should be the level of secrecy? This was the analysis that we have conducted. So you will find that whenever we are conducting any such analysis, there are three parameters, not only in ours, but in all other similar paper, you will find that there is a secrecy outage probability, one parameter. There is an intercept probability, and then there is a ergodic secrecy. So on these three parameters, the assessment of the performance is being done. So these are the mathematical formulations and their analytical solutions, and their you can say the verification by the simulation is something what was done over here. But every work is now more or less, we think that every work whatever we are doing, any model whatever we are doing, it must include the physical layer security aspect as well, because it has to be included in near future. So physical layer security is another very important aspect of the beyond 5G communication systems. Moving ahead, this is also something I am keeping it in the 5G plus. One important development has taken place from the deep learning application in the communication system. This is also something I'm very briefly introducing, because I have seen someone is speaking on this topic for the entire duration. Just I am introducing it, that it is such an important aspect. Artificial intelligence is something we cannot ignore anymore. In fact, communication engineering is no more traditional communication alone. A lot of information technology, computer science is required to be incorporated there. So this autoencoder based end-to-end communication system, it is also something over and above the Shannon's model which I was discussing. Up to the 5G, the standard Shannon model that we have been using, this is something, a different way of implementing the traditional system. So what you can see that in the December 2016, this was first proposed in a conference, and then in the general in the 2017 the paper appears in a IEEE transactions. So what we can see here, the traditional model has gone. The transmitter has some deep learning layers, and the receiver has some deep learning layers, and then transmission is done, and then receiver is done, and all this is based on the deep learning principles, artificial intelligence. So the traditional way of designing the source coders and channel coders, all those traditional techniques has, because now the optimization is done as per the deep learning principles, that is the neural networks or some similar technology. So if you have to transmit an M messages, so what was proposed here is you have to use okay, so this is something known as the single hot vector approach. This is just one approach. There are other approaches as well which are available. This example is for the single hot vector approach. So if you have to transmit m different messages, then depending upon your choice from 000 to 111, these are the possibilities. Whatever message is coming, you are required to choose that particular single hot vector, and all other vectors should be 0. So you are not transmitting the message, you are simply transmitting the corresponding hot vector. And this AI system at the transmitting end as well as the receiving end have already been trained for all of these different hot vectors for different channel conditions. So it's a trained model. So this trained model will once again pick up one of this hot vector, once again pick up the latest channel conditions, and then process this at the transmitting end and at the receiving end, such that different hot vectors are being generated with different confidence level. And the idea is simple, that whichever is the maximum, one may pick up. So you have transmitted this and you have picked up this, so it can be decoded into the respective input bits. So the message communication, message transmission and reception has been done without transmitting the messages. So this is how this system works, the end-to-end communication system works, where there are no specific source coding algorithms, there are no specific channel coding algorithms, there are no specific modulation techniques predetermined, but these all are selected by this artificial intelligence approaches. And interesting claims are being made. A DL-based communication system can be optimized for practical system over any type of channel without requiring a tractable mathematical model. This is very, very important. Because as the channel conditions are changing, we are saying, okay, the Gaussian model is not applicable. We need to go for the Rayleigh, we need to go for the Nakagami, we need to go for the Rayleigh, double Nagan, double Rayleigh, or so many models are there. And so many complex mathematical foundation is required to be developed for the traditional systems. But here, the claim is that without any tractable mathematical model, you are able to achieve the communications. The goals of the communications can be achieved without all this complexity. Simply, if you know the AI, you can do it. And this is also important because the counter argument was this, that what about the training time and testing time? Because we know that how the AI system works, it requires a lot of time. But the answer to the counter argument is this, that actually this mechanism is faster because a lot of parallel computing can be done in this implementation. So you know that this is something which was proposed in 2016-17. A lot of papers are available then after. Several pros and cons are being reported. Several interesting results are being reported. And if something, you can say, enough credible results will become available, then probably this may be a great change in the future networks. So it is something very interesting, very interesting developments. It is something which is going to change the entire communication system, the way systems are being designed and the way systems are being used. Now let us come to the topic where I left it on the front, on the first slide. What Professor Mehdi wrote, that level A problem has been solved, more or less has been solved, at least up to satisfactory level, it has been solved. Now we have to move towards finding the ways of implementing the communication system which can solve level B and level C problems. And the name given is the semantic information based communication. And semantic means a measure of usefulness, and definitely it is the end user who is going to define. And it means goal of the data exchange. This is very important identification. Whenever any communication is taking place, that communication is happening with a goal. So whether that particular goal has been achieved or not, this is something a very important criteria. So goal oriented semantic communication is something what is the requirement of the day. Particularly communication nowadays, including in the 5G, there is a lot of machines which are talking to each other. Machine to machine communication is there. Specifically for the machine to machine communication, this goal oriented communication could be very useful. In the semantic communication, actually what is being suggested and tried, that let us mimic the brain, how we learn and how we interpret the information. So the past actions as well as the accumulated knowledge, it takes place, it takes part in decision making. So semantic communication is something where the amount of information conveyed at the semantic level, the example we have discussed, you know that this is something what I do. So these are the important observations associated with the syntactic communication and the semantic communication. So the way it is being designed, or it is proposed to be designed, you can see it is October 2021. This model was presented in this Elsevier journal. So what is being suggested, that there is a source and there is a destination. Both of this source and destination are not empty person. Both of them are having the knowledge banks. Two machines are communicating or two persons are communicating. They are not the empty minds. they are having already some knowledge bank. So knowledge bank is always associated with each one of the entity of the communication system. And there may be some mechanism by which this knowledge sharing may be done through some back channel mechanism, if required, depending upon the application. So the idea is this source should take help from this knowledge base in generating a semantic message. And this should be part of the communication system optimization, which has not been there earlier. Communication starts from here. We take, okay, there is an electrical source which is generating, there is an information source which is generating the symbols. Now, what those symbols, does they have any semantic relevance or not? No one is talking about it earlier. And that is, we are starting from this point, level A, and we are ending at this point. Now, these boundaries are required to be enhanced. So not only this level, which is the semantic level, but up to this level, the task has been done or not effectiveness. So these are the three levels and the proper segmentations which are being defined in this particular model. So whenever a source has to transmit some message, then how that message should be properly worded, this should be coming with the knowledge base. And then appropriate message should be generated. And then this message should be converted into symbols, the way, maybe the standard way, doesn't matter. And then it is being transmitted from here to here. And similarly at the destination, we know that the message which is being coming over here, it is actually generated by a knowledge base, keeping this thing that I already know something. So the idea is same message when you want to convey to a specific person, you may like to use different symbols depending upon what the knowledge base is available here. So same message when you are trying to communicate to suppose some independent outsider person, you may like to choose something different, differently worded message. But if you want to communicate same thing to your friend, then probably the choice of words should be different. And you will find it actually very small messages, and sometimes even gestures only conveys the message. There is no need of transmitting anything. So this is something which is very, very important to understand, that this is something which is implementable. We know that what is the knowledge base I have. I know, or at least have a rough idea that what is the knowledge base available at the destination end. And if I know that this knowledge base is supposed to be used by that particular person, then I should accordingly design a very, you can say, accurate short message, because he will develop the entire thing at the destination. So there are two things which I was saying, that either one agent extracts all the concepts from the data set to communicate them to the other agent, or actually you are working on some minimal one. Both of these are the possibilities. This is a 2020 paper where one interesting observation is being reported. they implemented the semantic effectiveness plane over the definitely over the latest systems, the latest network where the humans as well as the machines are communicating. So there are users, there are sensors, there are actuators who are actually using the network, and all these are at the application level. So in the way the standard 5G system, how they should communicate and how much overhead they are creating. And when they are communicating through this SE plane, the semantic effectiveness plane, where user sensors and actuators are actually using the same system. System is still 5G. Through the SE plane, then you can see over here that a significant amount of reduction in the overhead at each one of this layer is being observed experimentally. In the year 2020, only this result has been reported. So this is the way, these are the experimental results which are available. And when you see and explore the different implementations, you will see that there are several different research groups who are trying different things for implementing this semantic communication. So that's all from my side. As of now, I tried to introduce a few promising technologies just by touching tip of the iceberg. Very introductory level I have introduced. If you have gained some interest in any one of these, then I request you to go ahead and explore those fields and do the research. So thank you so much.
Thank you very much, sir. It was a very informative talk, and I think participants would have hugely benefited from this talk. Sir, we have a couple of questions. So would you like to answer those questions? I will read out those questions for you. Yeah.
Sure.
Okay. So there is a question from Sheikh Razak. Can we replace amplify and forward relay with intelligent reflecting surfaces that may improve the energy efficiency and it might reduce the hardware cost?
Yes, definitely. That is the replacement. So depending upon the application, because when we are going for the amplify and forward system, then there is an amplification part involved, and then there is a broadcasting part which is involved. But when we are going for the reflecting surfaces, we are precisely looking for the point-to-point system. So we are trying to focus the transmission of the information to a particular person. So these two are two different things. So depending upon the application, we may replace, sometimes we may not replace, because what exactly we are looking for, we need to see.
Okay. And there is one more question from the same person. So which fading, whether it is Rayleigh or Nakagami fading, which is much suitable to estimate the channel information in practical scenarios?
Actually, this is also something which depends, because you need to see that in a given scenario, what is the characteristic of the scatterers. So depending upon those characteristics, actually you need to identify that which one is more suitable. So you cannot say that in some environment you need to go for the Nakagami with a different index. Sometimes you need to go for the double Nakagami. So it depends upon that what is the characteristic of the scatterers or the clustering of the scatterers that we are considering for that particular communication system. So there is no general uniform rule applicable for the wireless systems.
Okay. And what do you think about this Shannon's channel capacity? Like The people are trying hard to reach the Shannon's channel capacity. So what do you think about that? Like, what is your view on that? Like, practically, is it possible to?
Okay, so let me tell you that when Shannon's channel capacity is considered, the channel model in the system was considered as a AWGN channel model, and the system was a system where a wireline system was there. But actually, when we see the MIMO system, suppose where multiple channels are available and simultaneously virtual channels are available, then actually it has already surpassed traditional Shannon capacity. But if you just see that since now we are using the multiple channels, then some persons are saying that actually we should treat each one of these as a channel. So the Shannon capacity is also been multiplied. So this is the argument. But yes, if you go for the traditional system, you can see that there are different error control coding technique. You know that turbo code is there, and then there are different coding schemes. The way decoding is being done, we are approaching that particular limit for each individual channel. Let us see that when that limit can be achieved, minus 1.6 dBm.
Yes, sir. Thank you very much, sir. Over to Dr. Satish Tiwari. Yeah.
Thank you, sir. So, Professor Puri, sir, it was really indeed an enlightening talk, because I have been doing this presentation at different venues, platforms regarding this 5G and 6G, but never attended a presentation where I was supposed to see this technology from different perspective. That whether this AI and the advanced technologies, we are just going for it, or intentionally we are not looking at technology's drawback. So I have a question, a general one, that is there a trade-off between the technology and need of our society, especially after this geo era and this COVID. Now everyone is having smartphone, okay, and they are using most of the data or time in this video platform. So in that way, I mean, there should be some interference of the government or the higher authorities who are responsible person, that do we really need that technology for our society, even though it's good? We are just going for the technologies. Maybe we are skipping the other aspect, especially when a lot of people are talking about this cancer issues with the high frequency communication. So, sir, please enlighten us in this way, sir.
Yes, right. So this is really a genuine concern, and I must say that it is one of the reason that 5G is not being implemented at the higher 50 gigahertz and 60 gigahertz what it was originally proposed for, and that's why the benefits of 5G, which were projected initially, could not be achieved, because those objectives can be achieved only if you go for the 50 gigahertz or 60 gigahertz implementation. But these health concerns are really important. It really requires a thorough study before moving to those bands, and that's why people are trying to find out alternative technology that without going for those higher range, because EM wave is it itself is very difficult to understand. Even today, there is a lot of issues available with the physics experts. EM wave itself is very complicated. So when you are going for the higher side, specifically for generating those higher frequency waves, how it will affect the overall environment, that is a concern, and that requires to be addressed. But yes, as far as the technology is concerned, one need to see that actually we require a higher bandwidth, we require cheaper technology, and 4G has proved this thing, at least in India, that when you provide the data to the end user at a very cheap rate, then it can bring a lot of benefits in terms of the economy, in terms of the facilities, and several other things. So there is a trade-off. There has always been a trade-off. One need to see that what to do.
Thank you, sir. So, participants, do you have any question? Okay, no more questions. So we'll conclude this session. Thank you, sir, for accepting our invitation. It was indeed an informative and wonderful talk on the promising technology for wireless networks. I think your talk will be very beneficial for our participants, especially the way you have presented this talk. You have enlightened, you have covered the 5G enabling technologies. At the same time, you have forced us to think in from different perspective also. I once again thank you for your enlightening talk. Thank you, sir.
Okay, thank you. Namaste.
Thank you, sir. Thank you, sir. Yeah, participants, we have another session at 3:30, and it will be delivered by Professor Poonam ma'am from NIT Rourkela. She will be delivering talk on terahertz communications. So please do join that session.
So the next talk will start at 3:30. So you have like 15 minutes break. So thank you everyone. Yeah.
Unmuted. Good afternoon, ma'am. Yes, I cannot hear.
Yeah, good afternoon.
Yeah, and now we can hear you, ma'am. Yeah, good afternoon, ma'am.
Yeah.
Okay. So, shall we start?
Yes.
Okay. So, good afternoon. On behalf of SRM University AP and as a coordinator, I, Dr. Satish Tiwari, welcome you all once again to the Faculty Development Program on recent advancements in optical communication and wireless networks, organized by the Department of Electronics and Communication Engineering. In today's second session, Professor Poonam Singh will deliver a talk on terahertz communication. Dr. Poonam Singh is professor in the Department of Electronics and Communication Engineering, National Institute of Technology, Rourkela. She has teaching and research experience of more than 30 years at NIT Rourkela. She did her BTech and MTech from Sambalpur University and PhD from IIT Kharagpur in the field of wireless communications. She has published more than 80 journal and conference papers in the area of wireless communications. Her research interests are multi-carrier communications, spread spectrum modulation, 5G communications, millimeter wave and terahertz communications, massive MIMO, cooperative communications, etc. She has supervised 6 PhD students and 9 students are continuing PhD under her supervision. She is a senior member of IEEE, member of IEEE Communication Society, IEEE Vehicular Technology, life member of ISTE, and member of many editorial boards. Now I welcome Professor Poonam Singh ma'am to deliver her talk. Thank you, ma'am.
Thank you, Satish. Thank you for the nice introduction. Now I will share my slides.
Yes, ma'am.
So the topic of today's talk is terahertz communication. And as you know, the communication now we are going towards higher and higher frequency because of the bandwidth requirements. If you go for higher carrier frequency, then we can have more bandwidth. And at radio frequency and microwave frequency, already the spectrum is occupied because there are so many applications which require wireless transmission. And so there is always a scarcity of the bandwidth. So there is a proposal for millimeter wave communication and then terahertz communication. So the outline of my talk will be, we'll see some features, then what are the challenges in terahertz communication and what are the benefits, then a scope for research issues. So are you able to see the slides? Is it changing?
Yes, madam, we can able to see the slides.
So terahertz transmission is a complementary wireless technology for communication network. And this allows high-speed wireless communication beyond the optical range. So you can see, say this is an extension of the optical fibers for beyond 5G and also for 6G. So in order to achieve high capacity, the carrier frequencies now have to be increased so that you can have more bandwidth and so more capacity. Because as we know, the data rate is directly related to the bandwidth. So if we want to transmit at very high data rate, then we need to increase the bandwidth. And that is possible if you increase the carrier frequency. So if we can have a carrier frequency more than 100 gigahertz, we can think of the bandwidth in terms of gigahertz. Terahertz, as we all know, is defined as 10 to the power 12 hertz or 1 trillion cycles per second. And frequencies between 100 gigahertz to 10 terahertz have been proposed for terahertz communication. And if you calculate the wavelength, corresponding wavelength will be between 3 millimeter to 30 micrometer. So this terahertz lies in between radio waves and infrared signal. And it has some unique properties like terahertz can pass through some opaque bodies like plastics, textiles, paper, and cardboard. But it cannot pass through very thick wall, but it can pass through this type of materials, which are not very thick. And Terahertz transmitter is capable of transmitting digital data at a rate higher than 100 gigabits per second, using 300 gigahertz band. So this is much more faster than 5G. So Terahertz has been proposed mainly for beyond 5G systems or 6G systems. And the broad bandwidth of Terahertz frequency bands can be used for terabit per second indoor communication. So for outdoor communication, it can go up to 100 gigabits per second. And for indoor communication, maybe a few terabits per second. So we have, using Terahertz band, we can have wire equivalent wireless connections. So though the connection is wireless, but it is equivalent to wired, like optical fiber connection, where we can have a very high data rate. And these are very energy efficient. So we can design very small networks, micro networks, and nano networks. And
Excuse me, madam.
Will be energy efficient.
Excuse me, madam.
Yes.
Are you changing the slides? Because we cannot able to see that you are changing the slides.
Okay.
It's still in the slide number 3 for us.
Now is it changing?
Yes, now it's changing, madam. Yes.
Okay, but when I make full screen mode, I think it is not changing. Okay, so let us have in this mode.
Okay.
So we can see how Terahertz band communication helps in communication through different devices. Like if there's a device in a plane, or if there's a drone, there are some devices inside the building and some people are walking outside the building. All of this can be connected using a Terahertz band communication. Okay. And we can have terabits per second link between them. That means we can communicate through multiple devices at different locations at a very high data rate. So this is what Terahertz band communication aims to achieve. So some of the features, critical features are the capacity is very large and we can have extremely high data rates. But there are some problems also, like it requires line of sight propagation. So if there are some obstacles in between, then the communication may not be that good. Then Terahertz devices, they operate at in very narrow beams. And the frequency is close to optical, the wavelengths are closer to optical wavelengths. And as I said, it cannot penetrate very thick materials. So these are some of the problems. But they give some advantage also, because if the signal cannot penetrate through thick materials, then it will reduce the interference. So we have to take care of all this while designing a communication system. Then integrating this spectrum into wireless network will require some more stringent requirements for antenna siting and then backhaul. Then we also have to see the spectrum allocation policies, which are done by some international standards. There are some communication standards according to which these frequencies are allocated. So now they are limited to radio frequency below 300 gigahertz. And terahertz is used for greenfield communication. So how to allocate these frequencies, that is also important. Now, as we know, because the consumer expectations are increasing, we want to transmit more and more data at a very high data rate. And we also want that it should be everywhere, it should be connected. So the demand for ever more higher quality of service. Because of this, we need more and more bandwidth. then only we can have improved performance, improved data rate, and better connectivity. Then there are other requirements are like virtual IoT. We need all the devices to be connected through internet. Then this virtual reality, augmented reality, Internet of Things, all these applications, they require very high data rate. And 5G is supposed to cater to a wide range of applications, like starting from smart homes to smart cities. And also we want many recreational services, then some critical applications. So there are different types of applications which are required to be served. And 5G is designed to serve some of them, but still there are some limitations. So we can see what are the requirements as shown in this figure. There are two types of services basically. One is massive machine type communication, where we want all the machine to be communicated. So it is machine to machine communication or device to device communication. Like for smart home applications, we want all the devices inside a home should be connected to internet so that you can operate them from anywhere using Wi-Fi. It's sitting in the office, you can operate your, you can switch on and off your lights, your AC or geyser or anything. And similarly, we want a smart city application. We want more of machine to machine type of communication where each and every, you can say organizations need to be connected. And we want the information to be transmitted from, say, if there is an accident, you want that information to be transmitted to a hospital, to police, and to also the person's like family. So all these devices have to be connected, then only this is possible. So massive machine type communications is required for smart home applications as well as for smart city applications. And similarly, we need ultra reliable and low latency communications for different applications. Like for some examples are given, like 3D video or work and play in cloud, or any critical applications, self-driving car. So in this case, we want there should not be any latency. And the information has to be transmitted immediately, and it must be very reliable. So for all these applications, we have to design a system which must serve instantly. The data should be communicated, and also it may require sometimes very high data rate, sometimes maybe low data rate. So that depends on the application. So that is why Terahertz is communication proposes to give a solution. And as we can see here, the Terahertz spectrum lies in between microwave and infrared waves. And frequencies of the order of say 1 terahertz to a few terahertz. And if you calculate the wavelength, it is coming 300 micrometer to 3 meters. And here also we can see the spectrum allocation chart for different communication. Like for radio frequency, we have up to few megahertz to say 100,000 megahertz or 900 megahertz, practically, which is used for cellular applications. Then we have this microwave frequency range, and these are also used for different cellular as well as for Wi-Fi applications. Then we have infrared frequencies after transmission. So in between microwave and infrared, these frequencies are not being used currently. Now Terahertz communication proposes to use this band. And after infrared, we have visible light communication. So as you go, as you increase the carrier frequency, you see that the available spectrum will increase. Because if you take say 1 megahertz carrier frequency, then we can have a bandwidth of few kilohertz. But if we go for 1 gigahertz, then we can have a bandwidth of a few megahertz. And similarly, if you go in terahertz range, we can have the bandwidth of a few gigahertz. So it increases the available spectrum, and then also increases the throughput, because if you have a higher frequency band, you can transmit it at higher data rate. And it also increases the path loss. That is the disadvantage. And if you go for higher frequency, the path loss also increases. And if you are using lower frequency, then we can have more spatial coverage, but there will be more interference. And of course, it can be used because for mobile applications, because path loss is less at lower frequencies. So this is a summary of electromagnetic spectrum which are being used currently. So you can see the use of each of these frequencies. And in at high frequency, the main disadvantage, as we can see here, is path loss, high path loss. But as we know, the capacity increases directly with the bandwidth. This was given by Hartley theorem. The capacity or the maximum data rate that a channel can support is given by bandwidth multiplied by log 2 1 plus SINR. Or earlier we have read SNR, but when you go for multi-user communication, then interference is also a major factor. So it is SINR. So depending on the available bandwidth, the data rate can be increased. And we have seen that the capacity can be further increased by reusing the frequencies, like in a cellular system. And by reducing the cell size, we can further increase the capacity. We can increase the frequency reuse, and that helps in increasing the capacity. But there is an optimal value up to what you can increase. Like if you go on reducing the cell size, the infrastructure cost will increase, and the interference also increases. As the cells become closer, the frequency reuse becomes more repetitive, and so the co-channel interference will be increasing. So the challenges are most of the wireless applications are assigned in the frequency range of 1.4 to 22 megahertz. So this is a wide range. In this you will find many applications. And if we go for higher bandwidth, 60 to 160 megahertz, then it increases the complexity in the hardware as well as the cost also increases. And also, if you go for higher bandwidth, it increases the absorption loss, the scattering loss, and the penetration loss. So this will reduce the range. If the signal, if the path losses, if the losses are more, the signal cannot be transmitted over long distance. So after short distance, the signal level falls. So it can be used for short range communication, but not for very long range communication. And for this loss, for compensating these losses, we can use more bandwidth, more continuous bandwidth will be required. So that is again a problem because we have limited spectrum. So out of that, to get a wide bandwidth will be difficult. So Terahertz communication has many characteristics that we have seen, and the challenges are: one, as I said, high path loss. Second is low penetration power and low transmit power. The transmit power also at a very high frequency, we cannot increase the transmit power. So that is also low. If your path loss is more and transmit power is also low, then we have to improve the antenna gain so that the receive power can be maintained above the threshold SNR. And also we have to maintain the outage probability. So these are some of the issues that we have to take care while designing a Terahertz communication system. Now, high path loss is because this is transmitted at a very high frequency, and the path loss is proportional to the frequency. It is very sensitive to humidity also, and then the distance. As we have seen earlier, path loss is inversely proportional to the distance. So as the distance between transmitter and receiver increases, the received signal reduces. Even for 1 meter distance in terahertz spectrum, if you communicate a signal in terahertz frequency band, the total path loss may be 100 to 200 dB. And as you go higher in the spectrum, it can be more than 200 dB. Whereas for microwave frequency range, it is very smaller as compared to this. It is 1 to 2 dB. So that is a major problem. The path loss is very high at this high frequency, and that will reduce the throughput. Another problem, as I said, is low penetration power, because the signal cannot go through walls and other thick surfaces. So this will be a challenge for mobile communication, and the coverage will be less in this case. If it cannot penetrate through a wall, you cannot transmit the signal inside a building. And if there are multiple walls, then some partitions are there, then the received signal will further reduce. So this reduces the received signal power, and so it reduces the coverage area. The signal cannot be transmitted over long distance, because if there are some blockages, then the signal level will fall drastically. So if there is a line of sight communication, there will be no penetration loss, and so we can have a better communication link. So this is one criteria. We are using line of sight communication, we can improve the received signal. And also we can use non-line of sight, but it depends on the surface type. As I said, it can pass through paper or plastic or glass, but not through very thick partition. And also non-line of sight communication may be used where second order reflections can be used for transmitting the signal. Another problem is low transmit power. To compensate for high path loss, we need transmit power should be more. But at a very high frequency, it is difficult to get a high transmit power. So as you go higher in frequency, normally the transmit power used is less. And this is a typical value for a 650 gigahertz carrier frequency. A transmit power of -5 dBm is used, whereas for 800 gigahertz, 0 dBm is used. And as you go higher, it will be further reduced. So now if the transmit power is less and also the losses are more, we can improve the antenna gain. This will also increase the received signal strength. And the received power is directly proportional to transmit power and antenna gains, and inversely proportional to path loss. So we can improve antenna gain. This is inversely proportional to the antenna beam width. So if we want a high antenna gain, then we need very narrow beam width. And using a directional antenna, we can achieve that. We can transmit with narrow antenna beams, and this can increase the antenna gain by 27 to 45 dBi. Whereas for omnidirectional antenna, it is 1 dBi. So this is one advantage. We can have directional antenna, and because now we are going for MIMO and massive MIMO, there are a number of antennas, the transmitter as well as receiver. So we need to have directional antennas. And if they are more narrow, then it is better, because that will cause less interference to other signals. So by using this narrow antenna beams, we can also increase the antenna gain. Then outage can occur because when the power level falls below the SNR. And here, because there is low penetration power and there is narrow beam width, sometimes there will be a link failure, and that will cause outage in terahertz communication. So it can be either due to blockage of the signal, or it can be due to change in the device orientation, because now we have very narrow beam width. So if you change the device position or even its orientation at the same location, then also the received signal may fall. So outage may occur. And to avoid this blockage, to avoid these outages, we have to reduce the blockage. So non-line of sight communication should be used. If there is line of sight, then any blockage will reduce, will cause outage, because there is a transmitter and receiver in between. There may be some obstacles, or there may be some moving obstacles. Suppose a vehicle comes in between and it blocks the signal, so outage will occur. So it is better to have non-line of sight communication, where there will be signals through multiple reflections also. And still, even if there is some blockage, still you can receive the signal. And outage can also occur due to orientation change of the device or on the object on which device is mounted. Suppose you are holding the device in your hand, say cell phone, and if you change the orientation of that cell phone, then also it may go out of the beam width, and your signal level may fall and outage may occur. So these things we have to take care while designing. And to get higher antenna again, the antenna uses normally narrow wave width. So there should be perfect alignment between transmitter and receiver. Also, we can use it for small scale mobility, like inside the human body, we put some sensors and we communicate the sensors, transmit the signals to a device outside the body. So there we have a very small scale mobility. Here, even if the mobility is very small, still if the body is moving, that may cause some misalignment and outage may occur. So this mobility management is important in this case, when you are using very narrow beam width. So there are many advantages which are unique to Terahertz, and that is why it is being proposed for the future wireless communication. There are many limitations of other bands, so in Terahertz band we get many advantages, like it is a green field spectrum. It doesn't emit any dangerous signals which are harmful to human body. Then the bandwidth can be higher, as we have seen. Front and post is there. Security aspects, interference is less. Okay, green field spectrum and device. So then we can have scalability and backhaul support. Okay, we'll see each of this. So first is because of limitation of other bands, Terahertz band has an advantage. What are the limitations? One is they are fully allocated. The traditional lower bands are almost fully allocated for different applications. And it is very difficult to get a large spectrum. If you want to give any new service using large spectrum, that is very difficult to get. And even if you go for higher frequencies like millimeter wave frequencies, there also very not enough bandwidth is available. And then infrared bands are also susceptible to objects reflection and the noise source from the sun. Then there is also power restriction for safety, because at infrared, if you are transmitting, it can damage human eye. So these are the problems at high frequency in millimeter wave and in the infrared band. So Terahertz band has the advantage; it doesn't have this harmful effects for human eye or human body, and also we can get more bandwidth here. Then another advantage is green field spectrum. Terahertz is called green field spectrum because it provides, like we can propose some novel models. These are not being used for other applications. So we can have some new models at this frequency. Already some research is going on in Terahertz applications. And there are some restrictions, like This spectrum is used for some applications currently, like satellite service, Earth exploration satellite services, and then meteorological and spectroscopic. And here, critical users are this Earth exploration satellite services. So, but still there are many bands available for other applications. So we have to avoid coexistence with this applications. And if you leave this, then we get only less than 10 gigahertz bandwidth. Like if you want a contiguous large bandwidth, that is slightly difficult to get here also. But we can use spectrum sharing methods with this licensed applications. So when they are not using, the spectrum can be used for other applications. Similar to lower bands, here also we can have spectrum sharing methods. Like in cognitive radio, we share, and the same spectrum is shared by primary user as well as secondary user. So similar things can be proposed here also. And already some research is going on, and they are trying to get some standards. This in this band, 275 gigahertz to 3 terahertz. Then, as I said in the beginning, we can get a very high bandwidth in this terahertz carrier frequency, because the frequency carrier frequency itself is very large, so a wide spectrum can be obtained. That is the greatest advantage. As high as 250 gigahertz can be obtained. And as you know, the data rate is directly proportional to the available bandwidth, so we can transmit at a high data rate. Now we should have a system which can adaptively select the best spectrum ranges based on the environmental factors and other availability of the bandwidth. Then terahertz can be easily integrated with the existing lower band deployment. So this is important, because it should not happen that if you are going to install a new system, all the current system become obsolete. We want the existing system should be also be in use. And for that, the proposed system should be compatible with the existing systems. And this is how we can integrate the terahertz with lower and mid-band spectrum. So if you can integrate this, we can have like it can satisfy high user demands. Also, it can free up some spectrum in lower band. Suppose in lower band, some application is using a wide band, that can be shifted to terahertz, and the spectrum in the lower band can be made free. And small user demands can also be satisfied. If they want a very high data rate transmission for some small amount of time, this can be also served by terahertz communication. Then increase user coverage. So obviously the coverage can be increased. And at the edges also, the coverage can be improved. At the cell edge, normally the coverage is not that good, because base stations are normally installed at the center. So with terahertz communication, we can improve that edge with cell user also. Then it is interference friendly. Like in case of lower bands, like microwave bands, they can penetrate through the thick walls also, and so they can cause interference. But because terahertz communication has low penetration power and it has highly directional antenna, so the interference will be less. If there are multiple rooms and if you are transmitting to one of the room, the signal may not be transmitted to other rooms because of its low penetration ability. And because the range is also less. So after a few meters, the signal power will reduce, and that will reduce the interference. And we can also increase the spectral reuse in this case. If the signal level falls at a shorter distance, we can have more reuse, and thereby we can increase the capacity of the system. Now, due to dense deployment of these access points and user equipment, and the random directionality of the antennas, interference will be varying. So we have to calculate exactly what will be the interference in a particular system, and then accordingly we have to design. But of course, with terahertz band, the interference will be less. Then the security is also better because we are using directional beams and limited propagation. So this provides more secure wireless communication. And it can be made jamming resistant or eavesdropping resistant. So because if you are using directional antenna, the signal is only one direction. So even if there are signals in other directions, say at same frequency, they will not interfere with this. So this has also advantage in case of UAV, unmanned aerial vehicles, where ultra high speed and limited communication distance is required. And as we have seen in case of a spread spectrum system also, when you increase the bandwidth, this helps in reducing the jamming. So here also, because we are going for a very high bandwidth, so this will reduce the jamming, because if somebody is transmitting at a particular frequency, but the signal occupies a wider bandwidth. So even if some of the frequencies are affected, others will not be affected. So still we can get back the signal. So security will be better. Then scalability is also possible because so antenna size is directly proportional to volume, as we know. And so here we have very small antennas, as the frequency is very high. So antenna length may be 2 nanometers in size. And so dense deployment of antenna is possible. So this is an advantage for massive MIMO systems, where you need to deploy a large number of antenna and they are very close to each other. So if the antenna size is small, and because they are directional antenna with a very focused narrow beam, so it is easier to deploy those antennas at the transmitter or at the receiver. And this will also be cheaper. The antenna size is smaller, usually the cost will also reduce. So Terahertz is very much suitable for an ultra dense network. And also it is very helpful for body area network, where, as I said, inside the body you plant some sensors and they transmit the signals. So now you cannot think of having a large antenna in a body area network. So if the antenna size is smaller, it can be easily implanted inside the body, and the signals can be communicated. Then also we need backhaul support, and this is also important. So as we have seen in case of frontal, it is compatible with all the existing lower frequency bands. Similarly, it has a higher data rate compared to backhaul has a higher data rate compared to frontal. And we can have fiber optic cables. They can also be made compatible with this terahertz communication. So when you upgrading fiber becomes very costly, because there you have to change all the optical cables. Whereas if you can use a terahertz line without this fiber, then this will have some advantages over the fiber optical communication. So this will provide a wireless backhaul. Then there are many other advantages also, like It can be used for high-speed on-chip communication, and, on-site video streaming for public safety. Like if there is some accident or something, you can stream this information online, and immediately we can get the help or support from other departments. Then also scanning the human body for metals and concealed weapons, this can be done. And, spectroscopy and other applications are there. So it can be used to replace X-rays. This is also very important. For detecting weapons, we can use terahertz signals. As we know, X-ray is harmful to the human body, but terahertz is harmless to humans. And it can be used for detecting any unwanted weapons or concealed weapons without harming the body. So in any public event, if you need help, so a swarm of drones can be sent to the incident site, and they will send the information to the authorities, and they can monitor the situation. And, using this drones, the information can be transmitted quickly using terahertz communication. Also, it can be used in smart home applications for sensing the temperature, air quality of the object movement, everything in real time. So these are some other advantages. Now, what are the research issues? Because if you propose anything, you will get many research issues also. So these are some of the major areas where we can do research. One is design of test beds. So we need to perform more experimental evaluation, and channel modeling is required for terahertz communication. So for that, test beds are required. Then also antenna design is very important, because now the size has been reduced drastically, and we need a very narrow beam width. So the antenna design has to be changed accordingly. So most of the current research assumes a conical shape antenna beam, but now with terahertz we want different shapes for antenna beam also. Like you want some antenna pattern, particular antenna pattern, so we should be able to design the antenna for that, for a particular frequency. Then, as I said, massive MIMO can be used, because the antenna size has reduced and we are having narrow beam antennas. So this can be designed, and this will also reduce high path loss. If you are transmitting in a particular direction with a focused beam, then that will also reduce the path loss. Then we also need to design adaptive systems, which can adaptively change the parameters depending on the environmental settings. Like earlier, we have seen adaptive coding and modulation, how it is used to improve the quality of the received signal. Depending on the channel quality, you can improve, you can change the modulation scheme or change the coding rate. And accordingly, the data rate may increase or reduce, and the signal quality is maintained. So similarly here also, adaptive systems need to be designed. Then to avoid high path loss, access points should be placed strategically, like in an indoor setting, if you place access point such that there will be less obstacles in the path, so we can provide a line of sight path, and that will improve the received signal quality. So this is also important, how to put the access points. Then mobility management is also important. As we move higher in the terahertz spectrum, mobility management methods will become more complex. Because now, as we have seen, if you are designing for very narrow beam width antennas, so if the device moves slightly, there will be misalignment, and the received signal will not be in the desired range, above the desired decimal. So you may have outage. So this mobility management is very important. Then new access protocols need to be found, need to be designed. because terahertz is more sensitive to path loss and you may get frequent outage. So for that, new protocols have to be designed. Then the spectrum access, we need a regulatory body how to allocate this spectrum for different applications. Again, there will be licensed users and there will be some unlicensed users. So which frequency should be licensed band, which frequency can be given to unlicensed band, that is also important. Like in case of present microwave frequency, we know 2.4 gigahertz and 5 gigahertz, they are the unlicensed bands, also known as ISM band, industrial scientific band, and medical applications. For these applications, we have this unlicensed spectrum. So similar thing have to be done in gigahertz spectrum also. So after doing all these changes, we can provide data rate in terabits per second. And of course, then the hardware also need to be changed, because your hardware, the modulation, demodulation, the coding things, the filter design, everything should be designed to support the high frequencies. And also, there are some restrictions on electromagnetic radiation from the device. So those safety standards also have to be followed. So what is the EMR when a device is using terahertz communication, that needs to be calculated. And that will also help in finding what should be the transmit power. So these are the different areas where research can be done. So then we'll see the conclusions for terahertz communication. As we have seen, the current challenges and benefits associated with terahertz spectrum. And we see that there are many challenges which will limit the deployment of terahertz communication for mobile applications especially. But it can be used for very high speed communication. And this is a unique spectrum band which can provide higher bandwidth compared to the traditional radio spectrum, and also compared to millimeter wave communication. But the path loss is high here. So that is why this is not very suitable for mobile application. But for static applications, it will be more suitable. And compared to high frequency spectrum, like in case of FSO, the optical communication range and infrared communication, terahertz is not very sensitive to opaque objects, and it can pass through some thin layers, and it is also not harmful for human eyes. And it can provide very high demanding applications with 52 to 50 gigahertz bandwidth is easily available at terahertz carrier frequency. So if we can design methods to compensate for high path loss, then we can use terahertz for many applications, and we can get very high throughput. Though it is sensitive to blockage and mobility that we have seen, but so independently it cannot be used. For mobility, we will still depend on the existing microwave communication. But by using both lower bands as well as this terahertz band, we can improve the, we can have deployment of terahertz for many services, and we can improve the communication. So these are the main applications where it is proposed to be used. Indoor wireless access, okay, because in indoor the coverage area is less, so you can use terahertz communication for that. Then for there's an IO-BMP application. This is for body network. We can have Internet of things. Then you have a number of nodes in the body, and all of them are connected through internet. They can communicate, and a doctor can get the signals, multiple signals from the body, and accordingly he can treat the patient. Then it can be used with moving objects for driving machines. It can be used for flying machines. So these are different areas on which the research is being done. As we can see here, some of them. This is a Terahertz indoor wireless access. So here we can see that the wireless communication is done through Terahertz communication, and it can be, the signal is being transmitted through this thin layers. And so we can connect inside a building or inside a home, multiple devices can be connected using this Terahertz. So it provides an indoor wireless access here. Then similarly, we have some propagation measurements are being done in the lab using this Terahertz communication. And this is a setup for making the measurements. So as I said, a lot of research is being done. So they are doing these measurements. And for bio-cyber interface also, it can be used. So in body and on body, Terahertz sensors are there. Some are inside the body, some may be on the body, and all of them can be connected through internet. So this will help in diagnosis and the treatment of the patients. Then we have Terahertz band communication with moving objects. So if there are some driving machines, driverless cars are there, that can be supported by this Terahertz band communication. Then for flying machines, maybe the aeroplanes or the drones which are flying, they can also be connected through Terahertz communication. And they can help to improve the coverage. Okay. Then there are some special environments where this Terahertz band communication can be used, like the networks on chip. So in one chip you can have more than 200 CPU nodes, and all of them can be connected through wireless. You don't have to make all those connections here in hardware. So this is also where there is a lot of advantage in making this chip without wires. So up to 2.4 terabits per second network capacity can be provided. Because it is the coverage area is very small, so you can have a high data rate there. Then we can also have board-to-board links. So all these are like device-to-device or machine-to-machine communication. So a lot of research is being done in Finland, in University of Technology, then New York State University at Buffalo, Georgia Institute of Technology, in New York City, in Intel Labs, they are doing this. In Finland, in University of Oulu, they are doing the research. And these are some of the references.
Thank you very much, madam.
If there is any doubt, you can ask.
Madam, there are few questions, so I would like to read out those questions for you. So
Yes.
would you be okay, madam? Yeah. So the first question is, where exactly do you think that terahertz will be most widely used? So any specific application you have in your mind, like where, for this particular application, definitely terahertz is going to be the one that is going to be used. So
mostly it will be useful for indoor applications because there the coverage area is less. So and it will cause less interface to other rooms also. Like inside one room, you have an access point, you have multiple devices, they can be connected. And it will cause less interface to other rooms. And similarly, inside a body also. Like for smaller coverage area for any application, Terahertz communication will be good.
okay. In the case of indoor scenarios, like say for example, you have a hall with maybe like 50 people or 60 people. So will that be still possible to use terahertz communication? in that scenario?
Yes, it is possible because we here very narrow beam widths are used for transmitting. So
Okay, because
with narrow beam width,
it might-
20%, I think it can be easily supported.
Okay. Fine, madam. So you basically were saying that in outdoors it is not yet possible to use terahertz, but whereas in indoor communications it is possible
Yes.
to use it. Okay.
Because of high path loss, it is difficult to use it for outdoor communication, for long distance communication. But for short distance, it is good.
Okay, madam. So in case like if there are some interferences, what do you think about them, madam? Like still the terahertz communications will be fine. Like because of using higher frequency, it might lose its signal strength, right? So before it reaches the end user. So if there are some interferences in between, so will it be still you will be watching it for terahertz communications in that scenarios as well?
Yes, because there will be some blockage will be there. Ultimately, what we want is our received signal strength should be above the desired threshold SNR. Okay. So if there is some interference, it is acceptable, but it should not be very high.
Okay, madam. And there is one question from Dr. Madhusudanan. So
Yes.
how to manage interference level in heterogeneous networks while moving from lower level to terahertz band communications?
Yes. So that is a challenge because there will be different users, but because they are using different frequency bands. So we have interference in terahertz communication. You will have interference only use those from those users who are using terahertz bands. So even if there is a signal from other bands, that should not cause much interference.
Okay, madam. And one more question from Mani. What are the modulation techniques expected to support terahertz communication?
Modulation techniques, I think still research is going on, but we can use spread spectrum kind of modulation. Like you can go for any digital communication and then we can use spread spectrum to increase the bandwidth of the signal. So any other digital modulation like BPSK or any QAM can be combined with this spread spectrum modulation.
Okay, madam. Madam, there are a couple of participants asking the same question. So they are asking like if we will use terahertz in indoor, then the radiation effect may be more harm to our body. Is that right?
No, I could not understand. For terahertz communication, not really.
Yes, like when you are using higher frequencies, or so will it be harmful to the human?
No, that is what they have found, that infrared frequency is harmful to human body, but terahertz frequency is not harmful.
Oh.
That is why it is being proposed for even replacing X-ray.
Right, madam. Thank you very much, madam. So over to Dr. Satish Tiwari. Yeah.
Thank you, sir.
I think you are muted, Satish.
Okay. So, ma'am, the last question I wanted to ask, but in a different way. It was like, since I'm doing research in molecular communication, so researcher in this domain, they claim that this terahertz communication is not good in terms of that when this the wavelength of this communication will be close to the size of the cell. Yeah, wavelength of this communication will be close to that to size of the cell. In that case, it is not better option. That's why they go for another paradigm of communication. They call it smaller communication. But similarly, when I'm reading this paper on this terahertz communication, just to have knowledge, they are using the same for this again for IOBNT and body area networks. So still, ma'am, at my level also, I found that there is contradictory things. I mean, both are claiming that it can be used for this body area network. So, ma'am, can you throw some light, because still I am not having clarity in that context, because slowly I want to switch to this terahertz communication, but at that time I'm thinking that how I will motivate problem in that domain. If I am telling in this small communication that it's a disadvantage if you use this terahertz communication. Or it's, ma'am, debatable task, I mean, debatable topic, or it's there a clarity between this it's side effect of this Terahertz communication. That too, when we are talking about deployment of nano machine inside a body.
Yes, I have read in many papers, like it will not have harmful effects on body, on human body. That is why it can be used for body area network applications.
Thank you, ma'am.
If you have doubts, then we will have to do further research on this.
Yeah, ma'am, it's
Then
not like
only-
doubt, but see, when I'm reading the small communication, they always write that it's a benefit. I mean, we cannot use Terahertz communication for in-body communication. But similarly, when I'm reading papers, good papers in Terahertz communication, they're also telling the same thing. So there is a little bit contradictory
Yes.
things. Yeah,
Yes.
it will slowly, it will
Yeah,
it will take
slowly it
time.
will come out because this is a new area. So we cannot say anything with like guarantee that there will be no harmful effects or anything.
Right,
This
right.
is the new proposals.
Okay,
Still more
Thank you, ma'am.
research is required in this area.
Okay. So thank you, ma'am. There question more?
No. Thank you.
Okay. So thank you, ma'am.
And I would like to thank
well-
all the audience also for asking questions.
Yeah. So thank you, ma'am, for accepting our invitation. It was indeed an informative and wonderful talk on Terahertz communication. I think your talk will be very beneficial for our participants. And once again, thank you, ma'am, for your valuable time. Thank you, ma'am.
Thank you.
So participants, tomorrow also we'll be having the two sessions, one from 2 to 3:30 p.m. and another from 3:30 to 5 p.m. So please do join those two sessions also. And this is the schedule for upcoming 3 days. We'll have session only from 2 to 5 p.m.
Okay. Thank you. Thank you very much, everyone, for your attendance, and see you all tomorrow. Thank you very much. Yeah.
Ajay is asking some question. Why we are not paying his question? Who is Ajay Yadav?
Yeah, you can. What